Welcome to Spring LIB.
Fundamentals of Physics, Chapter 31, Question 47. For this problem, we'll determine some characteristic values for a very simple LRC circuit. The circuit itself is a serial loop with four components: the voltage source, a resistor, a capacitor, and an inductor with values as shown. This problem is broken into 5 parts. For part A, we'll calculate the resonance frequency, which is where the effects of the inductor and capacitor balance each other out, allowing for the greatest possible current flow in the circuit. The formula from the text is simply the resonance frequency, gamma sub d, and it's equal to 1 over the square root of L times C. When we plug in values for L and C, be careful to set all your units to their base values. Using microfarads here instead of farads will result in an answer that's literally 1,000 times too small. Finally, we can actually calculate the value for part A, and that's 224 radians per second is the resonant frequency for this particular circuit. For part B, we'll use the resonant frequency to find what the maximum current flow actually is. We start simply enough with Ohm's law, because this is an AC circuit, we'll use resistivity instead of just resistance. To calculate the resistivity, we actually need to account for all the components in the system, and we'll use this formula to do that. The resistivity is going to, here marked with a Z, is going to be the square root of the resistance squared plus the resistivity of the inductor minus the resistivity of the capacitor, quantity squared. And those resistivities are, the resistivity of the inductor is omega dL, and the resistivity of the capacitor is 1 over omega dC. So we plug those back in, and at this point we can plug some numbers in. And if you do that, you will get, depending on how much your calculator retained, you'll end up getting a number pretty close to 5, or maybe even exactly 5. The answer itself is actually exactly 5. And this is because this is an unusual situation. Normally, there will be some resistance provided by the inductor and capacitor portions of the circuit. But because we have an inductor that's has an inductance of 1 Henry, things cancel out. For those feeling ambitious, you can actually substitute the original formula for the resonant frequency in this part of the calculation, cancel out the inductance values of 1, and you'll find out that this whole term goes to 0. So our final resistivity is just 5 ohms. And if we plug that into Ohm's law, we find our maximum current is 6 amps. This situation is unusual, and in fact, the next couple steps we'll see where the resistivity is definitely not 5 ohms. Which brings us to part C and D. This part actually is looking for a maximum and minimum values of frequency where the current is half of the maximum current. And it uses the same formulation right up until the very end. So we're going to go ahead and solve them together. So we're looking for the upper and lower frequencies where the current is 1/2 of the maximum current. So we know what that is, 1/2 of the maximum current is from before. And we're actually going to end up solving for Z, because that's where where we're going to find the frequencies that we ultimately need to solve for. So if we rearrange to solve for Z, plug in the numbers, we end up with a total resistivity equal to 10 ohms. And now it's algebra time. We're looking for the two frequencies. We have a single formula, we have 2 frequencies. This is starting to sound like a quadratic equation. Let's see if we can turn what we know into a quadratic equation that we can solve for. We'll start by setting Z is equal to 10 is equal to R squared minus omega L minus, or plus the quantity omega L minus 1 over omega C squared. Then we'll go ahead and square both sides to remove the square root. We'll end up with 100 equals 25, etc., etc. And then I'm going to do two steps at once here. I'm going to subtract 25 from both sides. And I'll give us 75 equals 0 plus this stuff. And then I'm going to square root both sides to get rid of that square. And that gives us square root of 75 is equal to omega L minus 1 over omega C. And yeah, so we're almost there to where we can do this as a quadratic. Next step, I'm going to shuffle things around so I can set one side of this equation equal to 0, basically by subtracting the square root of 75 from both sides, and then multiply both sides by omega. And ultimately, we end up with omega squared L minus 8.66, which is the square root of 75, omega minus 1 over C. Since L and C are constants, we're good to go. In fact, we can go ahead and pull out the quadratic formula values for little a is 1, little b is negative 8.66, little c is negative 50,000. And again, this is the same situation as before. You got to switch your capacitance to farads before you start doing the math to it. Otherwise, you end up with rather different numbers. We can plug that into the quadratic equation thus and find out that we have omega is equal to 8.66 plus or minus the square root of 75 minus 4 times negative 50,000. And all of that over 2 times 1. And 75 minus 4 times negative 50,000 resolves to 200,075. So the next step is, since the part C asks for the lower frequency, we'll do the subtraction part. And we'll end up with a value, omega D1 is equal to 219 radians per second. And then we do the addition part to get omega D2 is equal to 228 radians per second. And that's parts C and D. Finally, part E, we're looking for the fractional half width using the supplied formula. So what we're looking for then is omega D minus D2 minus omega D1, and then normalized by dividing by omega D. This gives us a unitless number of 0.040 because we're dividing radians per second by radians per second. And this is basically the proportion of the original resonant frequency that spans the halfway point there. We don't actually need this for the problem any further, but you may come across that later on in other AC circuits. And this concludes the solution.